Good morning, everyone. I am Dr. V. Jayabalaji, Assistant Professor Mechanical, SRM Madurai College for Engineering and Technology, Madurai. So today my topic is equilibrium of rigid body, which is an important topic in engineering mechanics. So here we know that the external forces acting on a rigid body can be reduced into a force coupled system at any point O. When the force and the couple are both equal to 0, the external forces form a system that equal to 0, then the rigid body is said to be in equilibrium. Therefore, the external forces combinedly nullify their effect. In other words, all the forces, they will balancing themselves. So as a conclusion, when the force and the couple are both equal to 0, then the system is called in equilibrium. As we said earlier, the necessary and sufficient conditions for the equilibrium of rigid bodies are summation of forces, that is F1 plus F2, F3 up to Fn will be equal to 0, and summation of moment M1, M2, M3 will be equal to 0. The resolving each forces and each moment into an rectangular components, we obtain the forces summation of f of x equal to 0 and summation of f of y is equal to 0 and summation of momentum is equal to 0. Mainly the principle applies in equilibrium in these three parameters, f of x, f of y and momentum. Next, so this what we have seen for the plane forces. So when we are coming to the space, summation of f of x is equal to 0, summation of f of y is equal to 0, then summation of f of z is equal to 0. That is for 3 axes. And also for momentum, summation of moment about x is equal to 0, y is equal to 0 and z is equal to 0. So to write the equations of the equilibrium for a rigid body, it is essential to first identify all the forces acting on that body and then to draw the corresponding free body diagram. In a free body diagram, it is an isolated parts of the system or the system as a whole which shows all the forces acting on the system. So here as shown in the figure, all the forces F1 and F2, all the forces are acting on the system which is isolated part of system as a whole. These forces include all externally applied forces with the respect to the cell's weight, reactive forces at supports and forces exerted by the other bodies at the contact. So coming to this diagram, the sphere is rest on the wall and the floor and another small sphere with respect to the first sphere. Two forces are acting F1 and F2 at the top side. So here the bigger sphere it is acting at RA will at the point A will be RA and the smaller force which is acting at point C will be RC. Then weight, the overall sphere weight is acting towards downwards. So it is mentioned as RB. So we will see some particular cases of equilibrium. Equilibrium with a single force. The equilibrium is not possible under the action of single force unless the force itself is 0. For two forces, if two forces F1 and F2. So here in a body F1 and F2 are acting on a body and the body is in equilibrium, then the two forces must be equal in magnitude and opposite it in direction and it is collinear. So these are the two points in the equilibrium. The third point is for three forces. If three forces must be coplanar and they must be either concurrent or parallel. So this we can represent as a equilibrium. So here in this weight, three forces are acting at a starting from the single point. It is a concurrent system. So this system is in equilibrium. Next, there are two forces F2 and F3 are acting downwards and F1 is acting on upwards in a steel bar. So then this beam is said to be in equilibrium. So let us see one more examples for a rigid body in equilibrium. So here a weight is acting 98.1 Newton is acting downwards and a reaction is acting upwards, and from the wall a tension is acting towards the downwards. So here from the weight and tension the angle will be 110 degree. Then between the weight and the reaction the angle is 31.4, and between this tension and this reaction the angle is 38.6 degree. So for this system we have to find the tension, this tension and this magnitude of the reaction force. So here we can apply the Lami's theorem. So Lami's theorem states that coplanar concurrent forces directly proportional to the sine of angle of the other two forces between them. So here I am taking the first force as tension, then sine of angle of other two forces is 98.1 and are the two forces, the angle is 31.4. So T divided by sine 31.4. Then I am taking R divided by angle between these two forces, that is tension and weight. The angle between the two forces is 110 degree. Then finally coming to the weight is acting downwards. The angle between the other two forces is 38.6. So now by using this Lami's theorem we have to find the tension in the string and reaction in the point. So by equating the first and 3 we will get the tension. So first one will be E by sine 31.4, that is equal to 98.1 divided by sine 38.6. In this 1 and 3 only T is alone in variable. Solving this 1 and 3 finally we get the T is equal to 81.9 Newton. Then to find the reaction, equating 2 and 3, R by sine 110 is equal to 98.1 divided by sine 38.6. So there are only one variable in between equation 2 and 3. So we can find R. So solving this 2 and 3 we will get R is equal to 147.8 Newton. So by this method we can find the rigid body equilibrium for any given figure. So let us take one more example. A man raises a 10 kilogram joist of length 4 meter by pulling on a rope. Find the tension on the rope and reaction in RE. So what we have seen in the previous problem. So this is the joist, its weight is 10 kg. The man is pulling this joist by using a tension in the rope, by using the rope. So here we have to find the tension and reaction at point A. So angle between the rope and the joist is for 25 degree. Then joist and the floor is 45 degree. So here the three forces are concurrent and static equilibrium. By using this above method we can solve the tension and reaction in the given figure. Finally, by this method we can find the rigid body equilibrium for the given figure. Thank you.